Alrighty, let's do this. So we are now in week 13. 13 talks about heaps. Actually, no, hashes. Okay, so let's have a look at what hashes are and tell you all about it. I guess there's a video in there too. And some Google Docs. Okay, so first of all, hash tables are yet another kind of a structure, and it's the kind of a structure that is easier explained if you think of a dictionary. Okay, and what is a dictionary? Dictionary is kind of like an array, but except wherever we're going to be using it, instead of using indexes as numbers, we're going to be using indexes as words or letters. Okay. Some languages have a data structure called dictionary built into it. Like Python, for example, has a dictionary that is very easy to use. In fact, why don't I have a look at that class real quick so I can show you. And they just turned on a whole bunch of new ones for me. Alright, so let me show you what a dictionary looks like in Python, because it's easier to see since Python is a very easy language. Okay, so what's a dictionary? Here's an example of a dictionary in Python. Right, so you already know arrays, right? So arrays use, you have an array name, you have some square brackets, and then inside the square bracket you usually have like a number, 0 or whatever, something like that. Okay, well, what a dictionary is, it actually has its own word or letter. Okay, so what happens is you basically, instead of typing in a number to go to a specific element, you're going to type in a words to go to a specific element. And what's the advantage of this? Well, it allows you to jump directly to a specific element instead of going through all of them. So one of the disadvantages of a linked list was that you have to go through all the links in order for you to get to the one that you want. And one of the disadvantages of an array was it's hard to delete and remove. So this is kind of like, it's a fix-up for an array. Okay. So in this particular example here, just to show you a little bit of Python, right? You have this is your dictionary, right? We're creating an empty dictionary, and here we're just adding a couple of things to this dictionary. So the key corresponds to a specific element. So the word 2 corresponds to this Spanish word. The word 1 corresponds to this Spanish word. Okay, so you can easily pull the different elements by just using the actual keys. Okay, so that's what a dictionary is. And this chapter kind of explains this kind of things in C++ terms. Okay, so basically, there it is. It talks about converting words to dictionaries, and the initial approach that the book takes to do this is to, if I can zoom in on this, that would be nice. Okay, so basically what we're going to do is we're going to convert every letter to a number, okay, and we're going to have some kind of a algorithm to go from words to numbers. Okay, so every letter is going to have its own unique number. For example, A is going to be 1, B is going to be 2, C is 3, and all the way up to Z, which is going to be 26. Okay, so if you have some kind of a word, for example, like cats, you would give that word a numerical, an actual number. Okay, so for example, cats will be C is 3, A is 1, T is 20, S is 19, and then you just add up all these numbers, and then you get a word. Now the problem is that there's a lot of words that you can make up out of these 4 letters, maybe. Okay, stack. I don't know if that's how you spell stack. No, not really. Okay, but anyway, there's many different ways for you to, rearrange these different letters. Sometimes it might create an actual meaningful word. Sometimes it might be some just total garbage. Okay, so what we need to do is we need to have a more unique way to represent each of these combinations in a specific way. Okay, so what we're going to do is we're going to create a different way to do it. So basically, every word, every letter, the order of these letters is going to have its own number. Okay, so for just like we have the index 0, I mean the first element is 0, second element is 1. Same way, the first letter is going to be 0, second letter is going to be 1, etc., etc., etc. Okay, and what we're going to do is we're going to use powers. All right, so this is basically your representation for the word cats using another algorithm to create numbers out of letters. Right, so this is your first letter, which is the C, which is times 27 to the power of 3. Then the second one is the A times 27 to the power of 2. And then 27 is the base of 27 letters. We're assuming they're all lowercase, right? So the one all the way to the right is going to be the S, right? 19 times 27 to the power of 0. And then when we multiply all these different, letters and power factors, we're going to create some kind of a, number that is going to uniquely identify every word in the dictionary. Okay, but now the problem is that if you have some kind of a, for example, if you have a 10-letter word, and which let's just assume that it's all Z's, for example, then you're going to end up with some gigantic number that you cannot possibly make an array out of. Right? There's not that many slots in RAM for you to create an array of that many elements. So what we're restricted to now is, okay, we created a unique identifier for each of these words, but we got to fit them into an array of maybe 50,000 or 100,000 things, because that's as big as an array as you can have. Okay, and this is where hashing comes in, meaning that we're going to grab a big number and we're going to shrink it into a set of smaller numbers. Okay, and how we're going to do that? Well, that's exactly what hashing is. So the way it works is you're going to have some kind of a bigger number, and you're going to do the modulus operator on some kind of a smaller range of numbers. Okay, and just to remind you how this thing works, let's have a look at, that's Mark's old code. Let's get rid of it. All the way to main, and get rid of this stuff. Okay, so let's say, for example, we have some kind of a, let's say we have a int big num, okay, and the big number is equal to 100, okay, and then, well, the big number could change, so let's just abandon the big number for a second. All right, so let's say I have cout 6 modulus 3. Well, let's do 7. Okay, 7 modulus 3. See if you remember how the modulus operator works. Okay, what is this equal to? 7 modulus 3, right? And if you forgot, the question that we're asking is, how many times does 3 fit into 7? How many times? Twice, right? So 2 times, 2 times. So you have 7 minus 2 times 3, which is 7 minus 6, which is 1. Okay? All right. So that's how the remainder works. So let's do some other ones. Let's say I have 8 modulus 3. What are we going to get? 2? Right? Same question again. All right? How many times does 3 fit into 8? Right? It's still 2 times. So this time 8 minus 2 times 3 is 8 minus 6, right? And then you get a 2. So that's your remainder of 2. Okay, so this one here was 1, we said. This one here was 2, we said. All right, let's go to the next one. If I go to 9, then what? 0, right? Because there's no remainder at this point. Okay, if I go another one, grab this thing. Okay, and let's go to 10. What is it now? 1. Okay, and if I keep going and going and going, you're going to see that you're actually going to see the pattern. All right, so 11 modulus 3 is what? 2. All right, and if I do 12 modulus 3 is what? 0. All right, so whenever I have a modulus 3, what are the possible remainders that I could get out of it? It's either 1 or 2 or 0. Okay? And that was used when we make random numbers and stuff like that, right? Okay, so that's what the book talks about. That basically, if you have a big num and you have modulus, little num, right? The remainder is little num is a number between what? 0 to what? Little num minus 1. Right? It's basically you're going to get as many possible remainders as the value of little num, but since it starts at 0, then the actual values are going to go from 0 to little num minus 1. Okay? And that's basically how hashing works. Okay? So you're going to have some kind of a big number, which is going to be your possible number that you could have for a word in the dictionary. And in order for me to squeeze it into an array of 50,000, then what would my little num have to be in that case? 50,000, right? So if I wanted to have some kind of a big number that is going to be reduced to a smaller set of numbers from 0 to 50,000, then I would have to use a little number of 50,000. Okay, so that's how it works. But there are some issues with this thing, right? So the problem with that is that, as you can see in the little code that we have in here, you can have multiple ones for several different numbers. Several different big numbers can create or generate a remainder that is equal. Okay, that's how it works, right? So if I have a 0 and I do the modulus of something, it will go to 0. If I have a 10, it will go to 0. If I have a 20, it will go to 0, etc., etc. So multiple bigger numbers will translate to a smaller set of numbers that are the same numbers that are the same for different big numbers. Okay, so these in hashing are called collisions. Okay, and this is one of the drawbacks of hashes. So what we're going to do is we're going to have to figure a way to go around these different collisions. Okay, and again, the collision is basically you have a couple words that would map to the same identical place in the array. Okay, that we're trying to create. So for example, in this case, you have demystify and amelioration. God, I still can't remember what amelioration is. What's amelioration? I know it's important. Is that even a word? Ameliorate? Okay, so what is ameliorate? Make something bad or unsatisfactory. Now you know. Okay, maybe I'll remember it too. Okay, so that's the issue. So this is an example of a collision. A couple of different words are mapping into the same place in the dictionary that is already occupied. Okay, maybe. Okay, so there's different ways for us to deal with this thing. Okay, so one way to deal with this is called open addressing, which means that what we're going to do is we're going to try to fit this thing here, and if it doesn't fit here, we're going to go one down. If it doesn't fit there, we're going to go one down, etc., etc., etc. And the other way to do this is we're going to create separate linked lists that start at each of these places. So basically, if demystify is occupied, what we're going to do is we're going to create a linked list starting from this place, and every other subsequent word that maps to this location in the array will be linked after this first one that is in there. Okay, so that's the linked list approach. And there's also the open addressing, which means we're going to try to fit it somewhere. Okay, now one approach to this open addressing is called the linear probing. Okay, and what is a linear probing? I don't know if there's a picture in there. The linear probing is, like I said, we're going to start at demystified. We're going to try to fit amelioration there. It's not going to go there. We're going to go the one under it. It's not going to go in there. Then it's going to go the one after it. And then as soon as it finds an empty slot, we'll fit it in there. Okay? So that's an example of a linear probing. Okay? The problem with linear probing is that the fuller the table gets, the more of these different subsequent cells are going to be filled, right? So, and then if you have multiples of these, elements in the array that we're trying to filled already, that generates something called a cluster, right? So this is the example of a cluster here, right? So all elements from 27 to 33 are a cluster, okay? And clusters are bad, right? Because the idea behind hashing is you want to have a quick access and quick retrieval. You want to jump directly to a specific element, and you want to be able to retrieve directly a specific element. And if you have a cluster, then you pretty much almost end up having to deal with the issue of a linked list, where you gotta go and jump through all the different links to get to the one that you want to insert or the one that you want to delete, those kinds of things. Okay? So clusters are bad, and one way to eliminate clusters is, oh yeah, there you go. This is an example of a linear probe, right? And again, the linear probing can be used whenever you're trying to insert an element into the dictionary, and it can also be used whenever you're trying to retrieve an element from the dictionary. Okay?
Is this basically an array?
Yeah, it's an array. Yeah. And again, remember that there's different ways to do it. You can pretty much create the same thing with a linked list or with an array. It's really it's up to you how you want to implement it. Okay, so that's an example of a cluster and linear probing. Okay, now the next thing is, so this is an example of your find function in here. Okay, so what we're going to do is we're going to keep going until you get to the to an empty cell, and we're assuming that the empty cell will be signified. We'll store a null inside of it. Question?
Yeah, along the lines of the find. Let's say we're doing a linear probe,
Yeah.
and we're inserting values, and the first space is occupied. So if we're doing a linear probe, it goes to the next cell and
Yeah.
it inserts there.
Yeah.
Or let's say in this case scenario we had to go down 2 cells.
Yeah.
So when you go to retrieve it, then if you're searching for a hashed key,
Yeah.
how does it know it actually found the original one and not something else that just hashed to the same key? If you're looking for a cat and you're looking for a color, and they both hash to, let's say, 3, how does it know the difference? Because you're searching for, right there, it looks like you hashed the key already.
Well, you're looking for the data of. So remember that each thing that is you're looking for the data to match the key.
Data. Okay.
Yeah, you're looking for the data that is stored inside of the dictionary to match
But
the
if
key.
the data that was stored there originally has been hashed, I don't know how that's...
The data itself is...
wasn't the data originally hashed when it was put into the array? So I still don't see the uniqueness.
No, the hash value is basically so let's say the hash value is, let me go back to my Python. So the hash value is this, and this is the actual key. So what you're looking at is you're trying to use this to find a this. So don't think of this as the actual key. I think that's the misleading part here. So the actual key is the thing that's being hashed, and then once we hash that thing, right? So when we hash the key, we're creating this word right here, and then the actual key itself is this.
Oh.
So we're looking for that piece right here. Okay.
So the value of the array is not hashed. We'll use it to find the index.
Correct. The key is the thing that we're going to hash to create an index, and then based on that index, we're going to jump to the specific location, pull the data, and see if it matches the key.
Thank you.
Yeah. Good question. Okay. So that's how the search works basically. Okay. And an insert is very similar to this approach. Again, we have to keep going through this thing and keep searching for the actual empty spot where we want to insert this thing, and we're going to insert it in the place where it has a null, right? So, and again, of course, we're going to have to create an array and fill it up with a bunch of nulls, maybe, right? So that it knows where to stop. Okay. Now this is an example of linear probing, and I have the code in there for you so that you can type this whole thing and get it going. And it actually just uses arrays right? If you notice it, it's pretty much just an array of things, okay? But one thing that we're using here for the first time is we're using a vector, okay? A vector of data items is similar to creating an array of data items, except a vector can automatically resize itself, so it's not fixed in size. If you have, let's say a vector of two things and you try to insert a third thing, then the vector will just increase its size in a predictable manner. Vectors are not always, they're not necessarily a huge improvement over arrays. They're improvement in that you can expand them, but they have a drawback that the vector always will kind of increase itself unnecessarily big to what you need. So if you have, if you have a vector of, maybe 20 things and you try to insert a 21st, you don't want the vector to double itself to 40 things because you don't need 40 things. Okay, so that's one of the disadvantages of a vector. But there's also, array lists and things like that. Okay, so that's the reason we're using a vector in here, just so you know, right? So it's a slight question.
The hash table, what you showed him with, I came in a little late. So is it the Uno, what you basically the table? What does the table look like? Is it like just
The hash table?
Yeah.
Right, so the hash table, the best thing that I can explain is in terms of Python, right? So it's a dictionary, okay? So, and what is a dictionary? The dictionary is like an array, but instead of numbers, you're putting actual words, right? So that creates exactly what you see in here. It's an actual dictionary, right? So if I type in this thing here, then that's going to translate to this particular thing in my hash table. Okay, so the hash table basically is all these different words in it, and how we retrieve each of these words is using these keys.
And the vector holds that.
The vector holds a combination of both.
Okay.
Okay. Yep. Okay. And then going back to this here to tell you. So this is that. So you have to do this. Quadratic probing. Okay. So one way to eliminate this clustering of things, right, is to make it so that it doesn't just always necessarily try to fit whatever you try to insert into the next cell after, but to have it start increasing the probe every time, right? So for example, the first time it might go to 87, the second time it might go to 989, the third time it might actually go to 867. So we'll try to increase how much further and further it probes, so that it reduces these actual clusters. Because the more clusters you have, the slower the access and deleting of different things in the hash table becomes, and it becomes very inefficient. There's actually something called a load factor, and load factor is basically how many of these cells are occupied already versus how many of these cells are empty. If you have a hash table where the load factor is really big, that is not going to be a very efficient hash table. Okay, and even the quadratic probing. So the quadratic probing is basically the x. So the linear probe is you have a hash value, and then the next time you're going to try to insert somewhere, you're not going to try to insert at the same hash value. You're going to insert at a hash value plus step, right? And the step is always 1. So you're going to try to insert at 1, then at 2, then at 3, then at 4, then at 5. Okay. Well, the quadratic probing simply changes the step, so that instead of having step plus step and step increases every time, what you're going to do is you're going to take the square of this step, right? So the first time what you're going to do is, like before the linear was x plus 1, x plus 2, x plus 3, the quadratic probing is going to x plus 1, then it's x plus 4, then it's x plus 9, right? The 1 is just 1, the 4 is 2 squared, the 9 is 3 squared, the 16 is 4 squared, etc., etc., etc. Okay? So that's the idea between quadratic probing, right? So initially we do 1 step, then we do 4 steps, then we do 9 steps, etc., etc., etc. Okay? The problem with quadratic probing is that it does not always successfully eliminate clustering, because a lot of times what you're going to do is you're going to notice that the quadratic even the quadratic probing starts creating clusters of in a predictable way. Since it's always doing a 1 and a 4 and a 9, a lot of times if you have a lot of words that are translating to the same original value, they're going to end up creating like a certain type of a cluster. It is not as bad as the original linear probing, but it has its own issues associated with it. Okay? And that's where double hashing comes in. Basically what you're going to do is you're going to apply the quadratic probing, and then you're going to go and you're going to further hash the step itself. Okay, so you're doing one hash to create the key, then you're going to create another hash to modify the step in the quadratic probing if you wanted to. Okay, and then the separate chaining. Oh, and then one thing to watch out for this double hashing business is that what you can end up having is if you're trying to go to the end of the array, right? Like basically if the array is so full, let's say you have an array of 30 things and it already has 29 things in it, right? It will take a very long time to get to the empty cell, and what it will do is the step is going to get bigger and bigger and bigger and bigger, and you're actually going to do the index out of range thing, right? So you're going to try it, and in C++, you're not going to see like maybe necessarily well, in C++, a lot of times things are just not going to work. You know, maybe like what you were having an issue with, like half the code wasn't even showing, right? Because you just forgot a little plus in there, and it doesn't give you an error. It just actually the error was in the bottom of the program that said exit process 11. That wasn't as yeah. It would show part of it, and then the rest of it doesn't even show because that's just C++. You know, it's not very user friendly. It's not going to give you, hey, look, you did an index out of range or whatever, something like that, which is basically what was happening in your case. You were increasing one of them, but you're not increasing the other one, and then you were just creating an array of too many things, and then C++ just can't handle it at some point, and the program doesn't work the way you think it should, right? But the actual issue is that you're doing an index out of range. So again, the problem with this quadratic probing is that you could run out of space in the array, so you have to deal with the wraparound issue basically. So if you're
there, the unsuccessful one, is that what it?
What's that?
If you go scroll up, it shows like.
Yeah, so basically, let's say you have an array of 18 things, right? And then I did a 1 and a 4 and a 9, and I got all the way to the 18, but then maybe this one's also full, and then it's going to attempt to do another one, so now it's going to go to like 25, right? Okay. But there is no 25, so what do you got to do? You have to account for that thing, and you have to, you know.
Do you delete it? Is that?
Well, you have to deal with the wraparound issue, right? That's what we did with the queues and stuff like that. Remember, where we had a front and rear and all that. Okay, but the double hashing should eliminate some of those issues, because now the second time you do the hashing of the step itself, then you should try to reduce that to the actual size of the array. Okay, so that it never exceeds the space that you have for it. Okay, so that's the idea behind the double hashing. Keep it within the array itself, and also make sure that the clusters are not in a very predictable way. Okay. And by the way, a lot of times, or usually, the hash functions, if you look at the code that I had in here, if you look at the actual hash function, the hash function is not very long, right? It's just like it's a single. This is define, remove, insert. Look at the hash function, all the way at the top. It's one line of code. Okay, you have some kind of a value, and then you apply the array size to it so that it fits within the actual array. Okay? And a lot of times that's exactly what you want for a hash function. It's just a single line of code with the modulus in there. Okay? Now the other thing that I showed you, or that I mentioned already, was so other than quadratic probing, other than double hashing, we can also do the separate chaining. And that was basically if each of these cells is the beginning of a linked list, right? So if you have only one thing, well, that's the first thing in the linked list. If you have two things, then it's, you have a first link and a second link, and et cetera, et cetera, et cetera. And that eliminates somewhat, the issue of, clustering and the loads. Okay? And the hashing efficiency, it is very efficient as long as your table is, relatively empty. Okay, the idea behind hashing is you should be able to just have a straight access to the elements that you're trying to access, right? So it's the O1 time, which is a constant time. It's always as quick to insert as it is to delete. You know, just like you did with arrays, right? Accessing a specific element of an array is very quick. Okay, and that's the idea behind a hash table. Okay. And there's some formulas in here for the linear probing and for successful search and unsuccessful searches. So you can see how they graph, you know, in here. And the load factor is, again, how many of the cells in the hash table are already taken up versus if it's empty, right? And you can see in the beginning when the table is empty, it's always a constant 1, right? But the bigger and bigger this load factor becomes, it becomes infinitely longer, or exponentially and exponentially longer to insert a value, right? So if you have a load factor of 1, which is 100% full, you're never going to insert anything into the hash table, but it might end up going and trying to cycle through this probing forever. Okay, so the load factor of tables is very important to consider, right? So you need to make sure that you make your, come on, zoom out of this. Make sure that you make your hash table as big as it needs to be, okay? And there's some more formulas in there for you to have a look at how to calculate the actual load, how long it will take using this Knuth, okay? And the separate chaining, you can see the efficiency of that thing, right? It kind of starts, relatively easy again, and if relatively quick. Well, actually, it starts really quick at 1, and then when it gets to a load factor of of 1, it becomes very, very a lot more filled up. Okay, and the load factor is the number of things that you have in it divided by the array size. Okay. And that's pretty much, in a nutshell, hash tables. Okay, so let me have a look at this video that I have in here. Since I have it, let's have a look at it.
Before diving into hash tables, let's first review the pros and cons of some simpler data structures, starting with arrays. Recall that arrays allow us to store elements of a single data type contiguously in memory. Because each element is associated with an index or location, we have random access to all of the elements in an array. In other words, we can access any element in a single step by indexing into the array. This is a big deal because algorithms like binary search depend on random access. A downside of arrays is that their size is fixed. Because arrays store data contiguously in memory, you must specify an array's size when you declare the array. You are effectively asking the operating system to reserve the appropriate amount of memory for the array's elements. There's no guarantee that more memory adjacent to your array will be available for use later, so arrays cannot easily grow. Recall that we also learned about linked lists, which can grow because their elements are not contiguous in memory. Each node in a linked list contains the element we want to store, as well as a pointer to the subsequent element in the list. Unfortunately, the price we've paid for dynamic size is random access to elements. In order to access a certain element, it's necessary to traverse the entire list until the desired element is reached. So, if I'm looking for the number 9, I'd follow the pointers from node to node, checking whether the value of each node is equal to 9. As such, in the worst case, lookup is O of n, which is far from efficient. Can we do better than O of n while still allowing our data structure to grow over time? Hash tables offer a solution. Hash tables are used when speedy insertion, deletion, and lookup of elements is priority. In theory, insertion, deletion, and lookup can even be accomplished in constant time. So what is a hash table anyway? A hash table is just an array coupled with a function, which we'll call the hash function. The hash function takes a piece of data as input, we'll call this a key, and outputs an integer commonly referred to as a hash value. The hash value maps our key to a particular index in the hash table. You'd initially use the hash function to determine where in the hash table to store a given key. Later, you'd use the same hash function to determine where in the hash table to search for a given key. For this reason, it's crucial that a hash function behaves consistently and outputs the same hash value for identical keys. Know that hash tables can be used to store data of all types, but to simplify things, we'll focus on strings for now. Here's a simple hash function for strings. This hash function computes a hash value based on the first letter of the key. Apple begins with the letter A, so it's mapped to index 0 of the hash table. Similarly, banana is mapped to index 1, and cat is mapped to index 2. If a friend asks if the word dog is in the table, we'll input dog into the hash function, which will output a hash value of 3. Since dog is not stored at index 3, we can say with confidence that dog is not in the table, even though we've only checked one of the hash table's 26 indices. Time to throw a wrench into things. What if we want to store ant into the table as well? Ant hashes to index 0, just as Apple did. This is an example of a collision, the result of two keys hashing to the same index. Even if your hash table is larger than your dataset, and you've chosen a good hash function, you still need a plan for dealing with collisions, if and when they arise. Let's discuss the pros and cons of two common methods for resolving collisions: linear probing and separate chaining. With linear probing, if a key hashes to the same index as a previously stored key, it is assigned the next available slot in the table. So ant is now stored at index 3, since indices 0, 1, and 2 were already in use. And if we try to store a third word that starts with the letter A, it's assigned to index 4, since indices 0, 1, 2, and 3 are full. As you can see, even from this simple example, once a collision occurs, you significantly increase chances that another collision will occur in the same area. This is called clustering, and it's a serious drawback to linear probing. Moreover, worst-case insertion, deletion, and lookup times have devolved to O of n, as the next available slot could potentially have been the last slot in the table. Maybe separate chaining will offer a more compelling solution. In the separate chaining model, the hash table is actually an array of pointers to linked lists. When a collision occurs, the key can be inserted in constant time at the head of the appropriate linked list. What happens now when we search for Apple in the hash table? In the worst case, we must traverse the entire linked list, starting at index 0. The worst-case lookup time for a hash table that uses separate chaining is therefore O of n over k, where k is the size of the hash table. Wait a second. K is a constant, so O of n over k is really just O of n, which was the worst-case lookup time for a linked list. Have we really gone through all the trouble of learning about hash tables only to end up back where we started? That may be the case from a theoretical perspective, but in the real world, O of n over k could be a huge improvement over O of n. Think of it this way. Assume that k is 10. Would you rather wait 100 seconds or 100 over k, 10 seconds, for Microsoft Word to finish spell checking your document? As you just saw, resolving collisions entails one form of linear search or another, which slows things down considerably. Therefore, you'll want to choose a hash function that minimizes the chance of collisions occurring in the first place. Here are some properties of good hash functions to keep in mind. A good hash function should make use of all information provided by a given key in order to maximize the number of possible hash values. For example, if we had two strings, cat and caterpillar, we'd want them to hash to different places on the table. If our hash function only took into account the first 1, 2, or even 3 letters of the strings, a collision would occur, since both words start with the same 3 letters. Hash values should be spread evenly across the hash table. This will reduce the length of linked lists, should collisions occur. It's also a good sign if your hash function is capable of generating very different hash values for similar keys, making collisions much less likely. Our goal is speedy insertion, deletion, and lookup. The hash function plays a crucial role in each of these processes and will be called very frequently. Therefore, make sure it employs only very simple, quick operations to minimize runtime. I hope you've enjoyed this brief introduction to hash tables. My name is Lauren, and this is
And one thing to show you where this comes in handy is if you actually look at Md5 Hash. Right, and this is actually used. Hashing is used in encryption and password storing. So if you have, let's say, any computer that you have, when you type in your password, the password that is being saved on your computer is not saved as the original password, because somebody can just connect to the hard drive and look at the place where those passwords are stored and say, oh look, this is what the password is, and then they have access. Okay, instead, the password is encrypted using a hash. And one of these hashes, not too long ago, or some time ago, was the Md5 hash. Okay, so Md5 hash, come on, zoom in, is, let's say for example I do a hello, and you're going to see that this generates a unique hash for that specific word. Okay, if I have hello and then I have a hello with an uppercase, what she was just talking about was, for similar keys, your hash function should generate very unique and distinct hashes, right? So if I was to just go in there and change the uppercase h to lowercase h, this sequence of numbers in here should be completely different, right? So I go in there and I do lowercase h, right? Quite a bit different than the original one, which was this, okay? Another properties of hashing is that because of this hashing algorithm, it is impossible, if you have a good strong hashing algorithm, for you to go backwards from the hash to the original key. In other words, the only way for me to get to this is if I try to create some kind of a different key. Okay, so it makes it pretty much impossible to reverse engineer somebody's password. Okay. The only way for you to really hack a password is if you do the brute force hacking. Okay, and if you've taken my Python class, in there I actually do this kind of stuff. So if you want to take it, and you're going to see how brute force cracking works, because I have you do that exact thing. Okay. Yeah, and then a lot of the programming languages, they have these hashing algorithms built in. The Unix or Linux operating system, not too long ago, or several years ago, used this exact Md5 hash. But now there's a lot more other hashes out there available. Another thing about hashes is there's specific software out there, if you're interested in security and stuff like that, that have tables that have already generated all these different hashes for the different words. In other words, somebody went through the trouble to write a program that tested every possible combination of letters and numbers maybe that are in the English language to a table of all these different hashes, right? So that makes it faster for you because part of the process has been already done for you, right? The program that you're going to have to do for the Python class that I do is you're going to have to do the whole thing from scratch, right? You start with some possible guesses for a password, you arrange them in possible different ways, and then you look at every possible combination of words and letters and numbers, and you compare to see if any of those matches the one hash that you have somewhere. Okay, and if there is a match, if my guess corresponds exactly to this hash right here, if the word that I'm trying to hash matches the one that I have saved somewhere or have got somewhere, then I got the password. And that's really how brute force cracking a password works. Okay, so that's some application of hashing. So dictionaries, encryption, they're all it comes in handy. So what I have in there is, what you have to do for this is I have a little hash quiz that's going to test your, if you read, if you understood all this stuff, what are the different terms and how are they applied. And the other one is you have to do a hash table assignment, which is pretty much just get the program to work, right? That I have in there for you. get it going. If you want to, test your understanding, what you could do is you could try to change the linear probing to quadratic probing, right? So instead of having the linear probe go and jump by +1 every time, figure out how to, make it jump by more than 1. And then when you do that, you have to consider that, maybe you're going to run out of space in the array. Maybe you want to do double hashing, okay? Those kinds of things, okay? So that is what I wanted to tell you about hash tables. Do we have any questions?
For a wraparound issue, like, do you have to do the front rear thing like you would for a normal array? Or like for a list?
For the wraparound, you're more concerned if the hashed value goes in between, anywhere between the 0 to the size -1 of the array. So there's not going to be an issue about like going left outside of the array. The only issue is going to the right. So that's the issue to consider for the wraparound. Okay. So that's all I have for you. If you have any questions, send me your email. Come see me in the office. You know the drill. And we're almost towards the end of most of these important topics. Let's see what else we have left. So we're at week 12, right? The last couple of weeks are pretty much catch up, right? Last one is the finals week. The one before it, I'll let you catch up. So the only things that are left to talk about are heaps. Heaps are just this, a kind of a tree where, and it is a binary tree where the highest thing is either all the way at the top or all the way at the bottom. I mean, it's the highest thing is either all the way at the top or the lowest thing is all the way at the top. And so those are min and max heaps, and it's just a matter of how we arrange them. They're usually implemented with arrays, although they could be implemented with a linked list. And then we're going to talk about graphs, and graphs are basically, if you've done any kind of a math class, you should know what a graph is, right? So that's pretty much what a graph is, and it's you can think of it as as the broad category for all kinds of different trees, right? We can have a parent with multiple children, and these multiple children can connect to each other. So you can think of a map, and the cities connected on the map in terms of a graph. And the graphs are used for a lot of applications, just like we use them in math. And one application is to basically, let's say if you have a bunch of cities on the map and you try to figure out, okay, what's the fastest way to go from one city to the other city? Which route do you take? And that actually applies heavily on how routers work. So, the internet is just a collection of routers. They need to figure out, how does my packet that I'm sending from this computer get to the destination in the quickest possible way, okay? And then a lot of these routers, they use these graph theories to create routing tables so that you can packet travels the fastest way from point A to point Z or B or whatever, okay?
And
So-
heaps like the levels in the tree, kind of?
What's that?
The heaps, is that kind of how I saw when we were doing the trees, there's levels,
Well, here's some examples of graphs. Oh, are you talking about heaps?
Yeah, is that just a problem?
Heaps are basically a binary tree, but the way we are going to insert things in it is the algorithm to insert things in such a way that the biggest thing is always going to end up on top. That's a max heap. So it's just like a binary tree where each parent has 2 children. The rule here is that the parent is always greater than the 2 children, where the binary tree was one is less than, the other one is bigger than, right? So the relationship is slightly different. And then also the way that things are inserted, we don't go left, right, and try to find the value where to insert it. The way we're going to insert it, well, number one is we have to make sure that the biggest value is all the way in the top if it's a max heap, and then you have to fill up the bottommost level. So for example, this year we have 1, 2, 3, 4 levels. So at the fourth level needs to be filled up all the way in order for me to go and start working on the 5th level. So just the arrangement of how the structure is organized and where keys go is slightly different, but pretty much it is the same kind of an idea. It's a binary tree, but with a special kind of an arrangement. Okay, so that is pretty much what's coming, and and I'll make it easier for you. There's just a little quiz for that one, so just to test your understanding. So that's the plan of attack for the rest of the semester. Okay, so if you want me to cover anything else, if you're interested in anything else, let me know. If you have any questions, let me know. All right, you know the drill. And that's pretty much all I want for today.